Question 1 says find the current in the 2 ohm resistor using the Thevenin's theorem. Now, to apply this theorem, you are supposed to take the resistor in question out and then represent that terminal with an open circuit voltage. That open circuit voltage is called the Thevenin's voltage. So to illustrate, so we have our 5 volt source, our 3 volt source, our 4 ohm resistor, our 6 ohm resistor, and then our VTH. Now we can label the terminal, say A and B, and then choose a direction for the VTH. We can take the direction in this way, or you can take it in this way, but we will choose one to solve our question. Now, after assigning that particular voltage, the Thevenin's voltage in the circuit, we are supposed to now find that VTH, but we can see that no current is acting in this part of the circuit at the moment. However, we can use this part of the circuit to find the current because there is a closed loop over here. So if we assign a current here and say the current I is produced by this loop, then we can now choose this loop to find our current I. So summing voltages and voltage drops or EMFs, we have our 3 plus 5 equal to our I times 4 plus 4. 4 plus 4 because the current I goes through the 2 4 ohm resistors, meaning they are in series. So we have 8 to be equal to 8I. Our current I is therefore 1 ampere. Now, after finding the current I to be 1 ampere, we can decide to use this loop to find our VTH because we now have a current going through the 4 ohm resistor. However, no current goes through this 6 ohm resistor, so it will not be part of summing the voltages and then the EMFs in the circuit. So using this loop, we have our VTH plus 5 volt. 5 volts because it's in the same direction as the VTH and it's equal to 4I. So our VTH is equal to 4I minus 5. Since we have our I to be 1 ampere, our VTH is now equal to 4 minus 5, and that is negative 1 volt. Now, the negative means that the terminal B is at a higher potential than the terminal A. So now, finding our RTH, the theorem says that we short circuit all voltage sources and open circuit any current source. But since we do not have any current source in the circuit, it's just a matter of short circuiting the voltage sources and then representing the open terminal with our Thevenin's resistor. So we have our RTH over here, and then the terminals are still A and B. We have our 6 ohm resistor in the question, our 4 ohm resistor, and then this 4 ohm resistor. So now looking through any of the terminals, A or B, we can see that the resistor 4 is in parallel with this resistor 4, and their effective is in series with the 6 ohm resistor. So our RTH is equal to 4 parallel 4, and then the effective in series with the 6 ohm resistor, and that gives us our RTH to be 4 times 4 over 4 plus 4 plus 6. This is again equal to 16 over 8 plus 6. Therefore, our RTH is equal to 2 plus 6 equals 8 ohms. Now, since we are done finding the RTH and then the VTH, we can quickly put them into the Thevenin's equivalent circuit. Now, so putting them into the Thevenin's equivalent circuit, we simply find the current that acts in that circuit, and the current that acts in that circuit becomes the current that goes through the 2 ohm resistor. So drawing the Thevenin's equivalent circuit, we have this. Our RTH was 8 ohms, and then our load resistor, which is the resistor we took out of the question, or the one through which we are supposed to find the current, and then our VTH is equal to 1 volt. Now, I wrote 1 volt here because I've already indicated a negative sign here, because I'm going to choose my current I1 in this direction. So our I1 in that direction is equal to the Thevenin's voltage over the sum of the resistances in the circuit, that is the RTH and the load resistor. So we have our VTH, which is -1 over our 8 plus 2, and that gives us -1 over 10. Therefore, our current I1 is equal to -0.1 amperes. In this question, we are to obtain the effective resistance for the circuit below. Now, we can see that we cannot find 2 resistances having the same current going through them. So meaning no resistor or resistances are in series here. And we can also not go through any 2 elements without meeting a 3rd element. So you can see that this portion of the circuit has 3 elements, this portion of the circuit has 3 elements, this portion as well, and then this portion has 3 elements as well. So no 2 resistors are either in series or in parallel in this circuit. So we can notice that we have a star connection over here. So it is imperative that we convert this star network to a delta network. Then we can see that at the end we will have some resistors in series and others in parallel. So to illustrate, we have our voltage source, this resistor. We'll name the resistors as soon as we are done drawing. So now we can go ahead, name all the resistances. This is our 12.5 ohm resistor, our 15 ohm resistor, 5 ohm resistor, 20 ohm resistor, 10 ohm resistor, and then our 30 ohm resistor. So now we are going to convert this star network into a delta network, and to do so, we can name this resistor and say this resistor is R1, this is R2, and then we have this as R3. So what we are going to do is that we are going to find R1, R2, and then R3. To find R1, we can see that we have 2 resistors that are directly facing R1. So we have the 10 plus the 5 plus 10 times 5 divided by the resistor that we did not use, that's 20. And this will give us 17.5 ohms. Our R2 is equal to 5 plus 20, because those are the 2 resistors the R2 is facing, plus 5 times 20 over the resistor that we did not use, and that's 10. And we have 35 ohms for that resistor. Our R3 is equal to 10 plus 20, because those are the 2 resistors that we have, plus their product, 20 times 10 divided by the resistor that we did not use, and that's 5. And the result is 17.5 ohms. You know that.
But no, yeah, we will start here. No?
And then go say, do you have me in one?
I'll bring this in. Okay, start with the R3.
And now R3 is equal to 20 plus 10 So our R3 is equal to 20 plus 10 plus their product divided by 5, and that gives us 70 ohms. So we are going to clean the star network out. And then the resistances that came as a result of the star transformation. So now we can see that we can go through any two resistances without meeting a third element. So we can see that for this portion of the circuit, there are only two resistances, 12.5 ohms and then 17.5 ohms. Then the same thing applies to this side as well. We can see 15 ohms and then 35 ohms. And then this loop also gives us 70 and then 30. So 70 and 30 are in parallel. 12.5 ohms and 70.5 ohms are in parallel. 15 ohms and 35 ohms are also in parallel. So we have 12.5 ohms in parallel with 17.5 ohms. That's one. And then we have 15 ohms in parallel with 35 ohms. And then we have 70 ohms in parallel with the 30 ohms. So we are going to find the effective for this portion of the circuit, find the effective for this portion of the circuit, find the effective for this portion as well, and then put them on the outer branches. So 12.5 times 17.5 over 12.5 plus 17.5 will give us 175 over 24 ohms. Now 15 times 35 over 15 plus 35 will give us 21 over 2 ohms. Then 70 times 30 over 70 plus 30 will give us 21 ohms. So to put them back in question, we have our voltage source, and then we have this here as well, and then we have this here. So our 21 ohm resistor is here. We have our 175 over 24 ohm resistor, and then we have our 21 over 2 ohm resistor. Now we can see that our 175 over 24 ohm resistor and then our 21 over 2 ohm resistor are in series, and then the effective is in parallel with the 21 ohm resistor. So we have 175 over 24 plus 21 over 2 to be 427 over 24 ohms, and that is in parallel with the 21 ohm resistor. So we still have our voltage source, and then we have our 427 over 24 ohm resistor in parallel with our 21 ohm resistor, and that gives us our R, which is the effective resistance that we were asked to calculate, to be 427 over 24 times 21 over 427 over 24 plus 21, and that is equal to 183 over 19 ohms, or 9.63 ohms. Don't forget that we had 120 volt source acting in the circuit, but this is what the question asks us to find, the effective resistance, and we are done. And the final answer is our effective resistance, 9.63 ohms. However, if we were asked to calculate the current in the circuit, it's just a matter of dividing the 120 volts by the effective resistance that we calculated. So the I that will act in that circuit, say I is equal to the 120 volt over the 9.63 ohms, and that gives us 12.46 amperes. This question, we are to use the Norton's theorem to find the current in the 2 ohm resistor connected between E and F in the circuit below. Now, this is the resistor we are talking about. And now, to find the current through it, we are supposed to represent that branch with the Norton's current, IN. And then we can assign current in the rest of the resistors that we have, and then use KCL and then KVL to find the current. So to demonstrate, we have our voltage source, the resistor, another resistor, then we can pick any direction for the Norton's current, say this direction, then we name that IN. This is a 3 ohm resistor, a 2 ohm resistor, 5 ohm resistor, 2 ohm resistor, and another 2 ohm resistor. Then we label our voltage sources 7 volt and then 10 volt. Now, since the IN is found in this branch, we can assign currents from the sources and see the current I1 is produced by this source, and then the current I2 is also produced by this source. We can see that since I2 is produced by the source, we are supposed to apply KCL on this point and say that since I2 is entering this node and IN is leaving, then the current that enters this branch then becomes I2 minus IN. Now, over here too, we know I1 is entering this node, but the current that leaves this point is exactly the same as the IN. Then we can say that the current through this is I1 minus IN. We have satisfied KCL on this node as well. And then we can see that over here, since I2 is produced by the source, I2 is supposed to return back to the source. So I2 minus I1 will enter this node, and then I1 and IN also enters this node. So the summation is what goes through here, and that becomes I2 as well. In other words, the current that leaves the source is the current that returns back to the source. Again, over here, we can see that I1 minus IN enters this node, and then IN also enters the node. So their summation becomes IN, and that's I1, and that is what goes back to the source. So now we are supposed to choose loops to find our IN. How do we do that? Now, picking, we can see that we have 3 unknowns in the question. We have I1, IN, and then I2. So we need three equations containing these three unknowns. Then we can solve them simultaneously to find the value for in. We can choose the bigger loop G, B, A, H, J. That's G, B, A, H, G. And the equation that we can get from that loop will be, so assuming we are taking them in this direction, we are going to have our 7 plus 10 is equal to 2I1 plus 5IN plus 2I2. Therefore, we know that 17 is equal to 2I1 plus 5IN plus 2I2. And that gives us our first equation. Again, we can decide to choose the middle loop. We can decide to choose loop D, E, F, C, D. And then the equation that corresponds to that loop is, since we do not have any main source acting, it becomes 0 is equal to 3 into bracket I1 minus IN plus 2 into bracket I2 minus IN minus 5IN. So simplifying this, we have 0 is equal to 3I1 minus 3IN plus 2I2 minus 2IN minus 5IN. Simplifying this, we have 0 is equal to 3I1 minus 10IN plus 2I2, and that gives us our second equation. So in order to find the third equation, as I said earlier, since we have three unknowns, we need three equations so we can solve them simultaneously. We can decide to choose loop A, E, D, B, A. And then the equation that pertains to that loop is 10 is equal to negative 3 into brackets I1 minus IN plus 5IN plus 2I2. So simplifying that, we have 10 is equal to minus 3I1 plus 3IN plus 5IN plus 2I2. So then we can further simplify this and say minus 3I1 plus 8IN plus 2I2, and that gives us our third equation. So solving equation 1, equation 2, and then equation 3 simultaneously, our value for I1 using the calculator is going to be 13 over 6 ampere. Our IN is equal to 23 over 18 ampere, and then our I2 is equal to 113 over 36 ampere. So we have found our Norton's current to be 23 over 18 ampere. The next thing we are supposed to do is to find the Norton's resistance. In finding the Norton's resistance, we are going to short circuit all voltage sources and open circuit all current sources. But since we do not have any current source in the circuit, the approach becomes very simple. and then this place becomes, since I said it's the same as the approach of finding the Thevenin's resistor. So we have our Rn here, and then we have our 2 ohm resistor, 3 ohm resistor, 5 ohm resistor, 2 ohm resistor, and then the 2 ohm resistor. So if we look through this terminal, say A and B, we can see that the 2 ohm resistor here is in parallel with the 3 ohm resistor here. The 2 ohm resistor here is also in parallel with the 2 ohm resistor here, and their effective is in series with the 5 ohm resistor. So we can say that the Rn is equal to 2 parallel 3 plus 5 plus 2 parallel 2. Then we can say our Rn is equal to 2 times 3 over 2 plus 3 plus 5 plus 2 times 2 over 2 plus 2, which gives us Rn to be equal to 6 over 5 plus 5 plus 4 over 4. Therefore, our Rn is equal to 36 over 5 ohms. Now that we are done finding the Norton's current and then the Norton's resistor, all we are supposed to do now is to draw the Norton's equivalent circuit, and then we can easily find the current that goes through the 2 ohm resistor. How do we do that? So the Norton's equivalent circuit is the Norton's current being parallel to the Norton's resistor and then the load resistor. So we have our Rn here to be equal to 36 over 5 ohms, and then we have our load resistor RL to be equal to 2 ohms. The Norton's current IN, as we found, was 23 over 18 ampere. So we would like to find the current through this particular portion of the circuit, and so we apply the current division rule. The current division rule says that the current, say I1 in this circuit, or say I1 prime in this circuit, is equal to the resistor on the opposite side, that's 36 over 5, divided by the summation of 2 and the 36 over 5 times the current that is going to be shared, that's 23 over 18 amperes. So when we make this computation, the value for I1 prime then becomes I1 prime is equal to 1 ampere, and this 1 ampere is the current that goes through the 2 ohm resistor.